What's up? Yep. Actually, Dan just popped in.
Howdy.
Hey, how's it going?
Pretty good. I'm still out on the frying pan tower. So
Oh, wow.
36 miles offshore.
Did you get the diesel engine actually working?
We just did, actually, yeah.
Oh, just turned over. Nice.
Let me get my iPad hooked up here.
Okay. So most of the class likes to just stay on mute and ask questions in chat. I can read them out to you, or you can have the chat window open, whichever works.
I'll try to pay attention to the chat, but yeah, if you can call them out, that would be helpful.
Sure.
All right, so everybody can see my my whiteboard there.
Yep, looks good.
Okay. So thank y'all, and thank you, Craig, for having me. My name is Dan Schmidt. I'm the Director of Network Services and Telecommunications at Clemson. So my team is responsible for running Clemson's network and telephone systems. So that's everything that you use to get to the internet or whatever you're trying to do. Your packets are running on our network. So I have been working at Clemson for 24 years now, with a couple of breaks here and there. But I started as an entry-level network engineer, and I worked my way up. Even though I tried not to get into management, I really wanted to stay technical. It's sometimes hard to get good managers. So now I am the team lead, the director. So, but when I was, I guess I'd worked at Clemson for about 5 years, and I solved a complicated, what I thought was a complicated network problem with a piece of Cisco gear, and I actually found a hardware bug in the way a particular big, new at the time switch, a Cisco 6500, operated. And so I worked with Cisco and showed them how to reproduce the bug, and they said, wow, that's awesome. How did you figure that out? And so I showed them, and they said, you ever thought about coming to work for us? And I said, oh, my chest got all puffed out. And I went there, and I still had to interview, but their interview was, okay, Dan, your resume looks impressive and all, but what we'd like to see you do is to tell us how a packet gets from one computer across one network, across multiple networks, and all the way to some destination host. And if you could just draw out exactly how that works and don't leave out any details, that'd be great. So the wind is blowing here. Let me close these windows real quick. There we go. All right. I'm currently volunteering to work on an old lighthouse that's 36 miles off the coast of North Carolina, called the Frying Pan Tower. You can Google that if you're interested. It's pretty cool. We're working to restore it and keep it from falling into the ocean. So
it looks more like an oil rig than a normal lighthouse.
Yeah, it is actually a lighthouse sitting on top of a Texas Tower oil rig. That was it sits out at the end of Frying Pan Shoals, and it used to warn ships where the shoals were so they wouldn't run aground. Now ships have GPSs, so it's obsolete, but it's still very cool. So time went by, and I did get the job at Cisco, and ultimately I decided to come back to Clemson. But as it went on, you know, it really clicked in my head that, like, this is the best way to explain networking to somebody. It's the best way to tell whether somebody really knows about networking. So that's what I wanted to do today, is just to take you guys and we'll draw out a basic picture of Clemson's network and see if we can figure out exactly how a packet goes through the network with leaving out as few details as possible. We think of our computers working and packets flowing, they just usually do, but there's actually a lot of work that had to go into making that just happen. And in the field of networking, sometimes that doesn't happen, or something doesn't happen correctly. And you have to be able to troubleshoot that. And the best way to troubleshoot it is to basically become the packet, to follow the packet all the way through the network and figure out what each network element or device is going to do. So let's do that. Let's take a ride through the network. So first part of a network, got a computer here. Got a person using their computer, and that computer is connected with a wire, let's say, to a jack on the wall here. And then from the jack on the wall, there is a wire strapped through the walls and into raceways, and ultimately comes out in a network closet, usually down the hall somewhere. And in that network closet are a bunch of devices that we call switches. And these are metal box looking things that look sort of like a pizza box that has 24 or 48 RJ45 ports on the front of them. And these are called access switches. because they provide the access to the network. So you can see I'm using a wired connection. You're probably thinking, God, who does that? Well, the same network we bring out to jacks on the wall, and we connect wireless access points. And that's where your Wi-Fi comes from. So Clemson currently has about 7,200 access points on the network, and we connect them through the network in the same way as if you could plug your computer into a jack. If you want a really fast connection, plug into a wire, trust me, it's a lot better. So we connect to the access layer switches. And networks can be designed different ways. This is the way Clemson has operated our network since about 2007 was when we standardized on this design, and we've iterated on it a few times. But still, it's proven to be a pretty good design for us. So in the network closet there are a set of switches we call the distribution switches. And each access switch connects like so. And in the distribution switches, every building on campus has fiber that goes to rigs and to Strode. And we call that our campus aggregation. Sometimes people call those cores, we think a better term these days is an aggregation switch. It aggregates buildings. So every building on campus has got a piece of fiber goes to Strode, fiber that goes to rigs. Out of there, we connect to our 2 data centers. We have one in Pool Hall, and we have one at a building off campus we call ITC. And these are, so I guess I should say, distribution switches are slightly beefier versions of the switches that you see on the access layer. What's here? The aggregation switches are big, like mini fridge sized things. In our case, they're Cisco 7000s. In the data centers, we actually run Juniper switches. They're Juniper 10,000 series. So in the data centers, we have other networks into which servers are connected. We're just going to abstract those today with clouds. It's a whole other infrastructure that we operate, and it's kind of an automatically controlled network that works with the VMware software, so that networking just follows around the VM workloads wherever they need to go. Pretty cool. But that's out of scope for today's discussion. From the data centers, we then add a security layer, and that we have, these are supposed to be like bricks. These are firewalls, and these are network devices that provide policy layer. So they are up to a layer 7 aware device, and that's that's something we'll learn more about. The firewall is where we apply policies like what can get to where and that sort of thing. From the firewalls, we connect to the border. And this is where this is our interface to the rest of the world. In our case, we have borders at Pool and ITC, and they connect to various outside networks. Clemson actually runs its own called C-Lite. We have other ISPs as well. We'll abstract those with clouds. You have the rest of the internet out here, which we will abstract also as clouds. These are actually called autonomous systems. And they're connected in various ways as the internet does. And let's just say that somewhere out here is Google's autonomous system, and it's connected in some way. And inside Google's network somewhere is an actual machine that is answering www.google.com. I think I saw a question in the chat. Yeah, so you're asking, yeah, ITC is, I think it's 16 kilometers, so about 10 miles from campus. There is fiber that runs on 2 separate paths between the P&A building and ITC. And it's actually a great question. We use a technology called dense wave division multiplexing. We have 2 sets of those so that we can push multiple fiber optic signals over a single pair of strands. So
those are some of the coolest equipment we got. I love hearing about that stuff. The amount of bandwidth we can push through 2 strands of copper is ridiculous.
Yep. So DWDM is cool, and that you know, every device we've drawn up here so far understands what a packet is. Believe it or not, DWDM equipment does not understand this. It's only it works on the physical layer only. So it takes a light signal in, converts it to another wavelength, so a slightly different color of light, and then sends essentially a rainbow down the fiber. And then on the other end, it splits it back out again. So they're optical devices. And as far as the routers know and the switches know, they are directly connected. So pretty cool technology. We also use that. We operate our own DWDM network between Atlanta and Charlotte called C-Light. That's where we get the majority of our external connectivity. That way we're able to be in Clemson, which is 2 hours from anywhere, and have you know, very robust connectivity to the outside world. So so here we are. So we have now drawn out a network. I'll scooch this over like this. And what our question for the day is, can we figure out if we want to pull up, on our computer right here, that I'm just circling in yellow right there, we want to pull up www.google.com on the other side. That's all we want to do. So to get a packet from our computer all the way over to google.com, let's see if we can trace through and figure out exactly how that happens. And please, when I do this in person, I want you to kind of deduce through this and figure this out. You guys maybe have seen some networking, maybe some of you have taken Computer Science 3600. I taught that one semester a few years ago. We learn about networks. So let's try to use some of that knowledge and see if we can deduce this. And a lot of times it doesn't make sense until you actually try to put it in practice. So that's what we're going to try to do. And this is the way, if you told a network engineer that a network was broken and you couldn't get to www.google.com, that person would start tracing through and thinking about it just like we're going to do, in my opinion, if they're a good network engineer. So, all right, so on our computer, we have to build a packet. And we're going to represent a packet. Let's see, zoom in a little bit here. We're going to represent a packet. A packet is nothing but a big blob of data. In reality, it's nothing but a bunch of ones and zeros in a particular order, right? So as it turns out, the order of how things go into this packet are essential. So there's this thing called the OSI model. Are we familiar with the OSI model? I hope so. Normally I'd be looking for some odds. Good, yes, excellent. All right, so it's a 7-layer model, all right? 7, 6, 5, 4, 3, 2, 1. Hang on, now it's raining. I gotta close the window again. All right, so let's go through all these layers, and you'll see why in a minute, so bear with me. We have layer 7. Anybody know what layer 7 is called? Application, that's right, exactly. All right, how about layer 6? It's the presentation layer, exactly. And I mentioned I'm not a network engineer anymore. I'm a manager, so all I do is go to meetings and write emails all day long. So you guys are going to have to help me through this. So, but we'll see if we can work it out together. All right. So let's see. Layer 5 is one we don't talk about too much. It's the session layer, exactly. All right, and layer 4 is we're getting into networking now. That's the transport layer. All right, layer 3, that's my favorite layer. What's that? That's the network layer. So this is the layer that tells us how to get between multiple networks. What about layer 2? What's that? Data link, yes. And layer 1, also one of my favorite layers, physical. Yes, exactly. So let's put all this together. What does this really mean? In our case, we're wanting to pull up a web page. So our application could be Firefox, which is rendering HTML, which is being sent via what protocol? HTTP, all right, which is over TCP. And what type of network layer are we typically using? IPv4, very good. And data link, in our case, what is our data link layer here? It's twisted pair Ethernet. And physical, in our case, is actually twisted pair copper. So we have the physical network, you know, at least for our computer, is copper over Ethernet, transporting IPv4. So you can see how this whole OSI model fits together. Well, guess how a packet is assembled? It's assembled in that order. So the very first bits in a packet are the data link headers. So it's a bunch of 1s and 0s arranged in a particular manner. So if we start dividing this packet up here, like so, this is the data link layer of the packet, layer 2. This is layer 3. So we got to start filling in some addresses here in our packet. So at the very end of our packet, we have our actual HTTP 1.1 get / or something like that. Whatever it is that a web browser asks for is actually what is being sent to the web server. But we got a bunch of stuff to fill in this packet in order to be able to put it into the network and get the network to actually transport it over to Google for us. So at layer 2, we have destination Ethernet or MAC address. We have source MAC address. layer 3, we have destination IP address. Looks like our power went out, but the network fortunately keeps working when that happens. We have destination IP, and we have source IP. And in this case, this layer 4 is, what is layer 4 that we're using in this case? It's TCP, right? So TCP, amongst other things, tells us about a port number, and in our case, our port is going to be 80. Of course, TCP does many other things. It's a protocol that actually ensures that the data gets transferred. So speaking of that, let's go back to our OSI model. We used a few examples over here. TCP we were just talking about. What's another common layer 4 protocol? Anybody have any ideas? UDP, yes? Why would, and so UDP is an interesting protocol. So TCP uses a 3-way handshake to verify that data gets from one side to the other. UDP uses no such thing. Why would we, and so sometimes UDP is called an unreliable protocol. Why would we want to use an unreliable protocol in networking? Video streaming, exactly, right. So if some packets get lost between me and you guys going across the ocean, they're gone. So Zoom's just going to fill in with a blank or a stutter or something like that. So there's no sense. It either got there or it didn't. It's for real-time uses. What about layer 3? We're talking about IPv4 in this case. What's another layer 3 protocol? IPv6, thank you. In olden times, there was another one called IPX. There used to be another one called AppleTalk. When I first started working in network services, we supported AppleTalk, IPX, and IPv4 on our network. Today, we only do IPv4 and IPv6. What about data link layer? What are some different data link types? So some examples might be Wi-Fi. In the olden days, there was token ring, FDDI, ATM. Those are all dead. Pretty much everything today is Ethernet. Physical layer, of course, we have copper. What are some other physical layer things we could use? Like fiber, air. Could run our own protocol. We could do it with smoke signals. Doesn't matter. It's kind of the cool point of this whole layering thing is that you can come up with different protocols at different layers and in many cases get them to fit together. So back to our packet. We've got to fill in destination MAC address, source MAC address, destination IP address, destination source address. Some things there might be a little mysterious, so let's fill in the stuff that we can probably figure out. So let's start at layer 3. What goes in our source IP address field? That's the address of our computer right there. Where did that come from? So that is an IP address that could have been obtained automatically. Does anybody know the protocol that handles that? It's the Dynamic Host Configuration Protocol, or DHCP. When you turn on your computer and it gets an address, we actually run a set of servers that hands you an address, checks it out of a database, and gives it to you for a length of time. Another way is that you could have a statically assigned IP address. You know, when I first started working in network services in 1998, the DHCP protocol, believe it or not, didn't exist. And the way it happened was I'd answer the phone and say, network services, this is Dan. They'd say, hey, Dan, this is Ken over in biology. I just got a new computer and we want to see if we can get it on the internet. And I'd say, oh, cool. And I'd say, all right, well, I would hand him an IP address a default gateway, and DNS information, as well as subnet mask, and he would put it all in there. We'll talk about what all those things are. So let's keep it simple so that we don't have to explain how DHCP works today, and just say that I have a statically assigned IP address. So I'm going to say that it's 130.127.4.22. What about destination IP address? What goes in there? So in our case today, actually, it needs to be whatever the IP address is of this thing over here at Google, right? So how do we get, we have www.google.com. What is the protocol that tells us what IP address that is? DNS, the domain name system. So yes, we have a protocol for everything in networking. Anything we want to do, we have a protocol for how you do it. A protocol is nothing but like when you and I meet, I say hey and you say hey. That's protocol for how we introduce ourselves. So in networking, protocols are just the way we get things done. So we use DNS and we query. Can anybody pull up a terminal window or something and do an NS lookup on www.google.com and tell me what the IP address is currently to get to google.com? One seven two 217.13.228. Notice you guys are getting different ones. I kind of made up the last little bit there, but good enough for our purposes. All right. Layer 2, data link layer. Data link layer is the thing that gets us from a single point on the network to another single point. In this case, so it gets us from our computer here to the edge of this distribution switch right here. That's all layer 2 does. So let's again start with what we know about. What about our source Ethernet or source MAC address? Where did that address come from? Anybody know? It comes, so the answer is it comes burned into your Ethernet card from the Ethernet card manufacturer. You can also assign it yourself. That's usually not recommended. But it's a 48-bit address, usually represented in hexadecimal. So in our case, we're just going to abbreviate it, and we'll say that our source address is BB22. What about our destination MAC address? Do we put the, do we somehow determine what the MAC address is of that server way over on Google's network? Do we somehow figure out what its Ethernet address is? Do we do that? The answer is no, we do not do that. That's right. Very good, thank you. So what address, in our case, what is the destination? We have to put something in this packet. We can't send a packet without a destination MAC address. What MAC address do we put in there? Any ideas? Somebody, I think, sort of mentioned it, that you put the next hop LAN in. So yes, Ben, that's exactly right. So in our case, the way Clemson's network is laid out is your default gateway is actually here on this distribution switch. So in our case, one of the things that I told Ken when he gave me an IP address was, or when I gave him an IP address, was that our default gateway was 130.127.4.1. We arbitrarily choose to use usually number 1 as the default gateway. It could be any number on that subnet. And so then we know what the gateway is, but we need to now know the MAC address of that. And somebody mentioned that we use a protocol called ARP, the Address Resolution Protocol. But a question for you. how do we know logically that www.google.com is not sitting on our local network? How do we know that we have to send it to the default gateway? I mean, you and I know it's not sitting on our local network, but we're human beings. Getting there, there's got to be a way that a computer, yeah, magic. Basically, it's actually a lot simpler than that. So there was another thing that I gave Ken when he asked for this IP address, and that was the subnet mask. And that was something that looked like this. Three 255s and a 0. So the question now is, what is a subnet mask, and how does it help us determine whether whether a computer is on our local network or not? Well, so we know that an IP address, I haven't mentioned this, but maybe you know this, that an IP address is actually made up of how many bits are in an IP address? IPv4 address, yes, 32 exactly. Anybody know how many bits are in an IPv6 address? More. 128. So the address space is ridiculously expanded with IPv6 and insanely constrained in IPv4. We've been out of IPv4 addresses practically since 2011. But we can't seem to move on. So partially because of people like me who keep talking about it. So one of these presentations, we're just going to do an IPv6 one. So, but in any case, if we think of each one of these dots here, dotted quads, those are each how many bits? They're each 8 bits, right? So if we take 255 and we convert it to binary, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. That's the subnet mask represented in binary. You can also convert 130.127.4.1 into binary. You do a logical AND on that. And that tells you basically that the first 24 bits of this network of this IP address represent the network, and the final 8 bits represent the hosts. So this is what we call also a 24-bit network. So the modern day notation is CIDR, CIDR notation, classless interdomain routing, is a /24. It tells you that the first 24 bits represent the network, last 24 bits represent the host. Since we see that 172.13.228 is not inside of 130.127.4, we know it's not on our network. So our computer then knows, okay, in order to build this packet, I have to put in the MAC address of the default gateway, and it uses ARP to do that. If it did that logical AND comparison and found it was on the same network, it would ARP for that, and it would put the actual MAC address of that actual computer on the local network in there, and it would just go directly to that computer without passing through a router. So does that make sense to everybody? That's an important concept here. And Craig, feel free to interrupt if I start missing something. But let's just say that our destination is CC11. So here we have DB or BB 22, and our default gateway MAC address is CC11. So now we have built a packet, and we are ready to put it out on the network and see what happens. What order do you suppose this packet is transmitted out onto the network? With the which end first? It's a sequence of ones and zeros it's going to send. Which end is going to go first, you think? Yeah, so it's going to go into the network in this direction. So the very first thing that's going to feed into the network switch is the destination MAC address. Convenient, because that's what this switch has to make a decision based on. So let's zoom in a little bit here and think about this access layer switch here and what it does. What does it do? So I send a packet in this port. How does it know? We can look at our drawing here and we can see that it's going to go out one of two links in order to get to our distribution router. But how did it learn that? So, and let's also assume that this switch, this access layer switch here, I just turned it on. It's never seen a packet. This happens to be the very first packet that has ever come into it. So how did it learn where the upstream path is to CC11, our destination MAC? It's a good try, but no, that's not what spanning tree does. Spanning tree helps it finds loops in layer 2. Broadcast flooding, Ben, you got it. That's exactly right. So this access layer switch has got inside of it a table. And it has port and address. Other stuff too, but in our case, we just turned the switch on. So this table is empty. And so we don't know what to do with it. So Ben answered that what it does is it floods. So this packet comes into the switch. It looks to see, is it in my MAC address table? If it's not in its MAC address table, what does it do? Ben said flood, but what does that mean? Sent out on all interfaces, almost. It sends it out all interfaces except which one? The one that it came in on. That's exactly right. So that packet comes in this port and it gets sent out every port. That way the switch knows that it's definitely going to get somewhere. A switch is not allowed to not carry a packet. It has to move the packet. It's a hot potato. It's moving it. It has no choice. Routers, we'll talk about later, have a choice and they don't have to forward packets, but a switch does. In fact, the name switch is actually a marketing term. These devices were originally called learning bridges. So a bridge was a device that bridged a gap between two Ethernet networks. An Ethernet network in the beginning was actually a segment of coax cable. And when you wanted to get on that Ethernet, you actually tapped into, you drilled a hole in the coax and you tapped into it. And so everybody in your hallway typically would be on, literally on the same Ethernet segment, same segment of coax. And then those segments of coax would be separated by bridges. Well, eventually, and bridges were very expensive originally. So, but time went by and the network manufacturers were like, well, heck, we can just put everybody on a switch port or everybody on a bridge port. And so they came up with the term switch, but the function of the bridge is still the same, learns MAC addresses. So how does it learn the MAC addresses? See a question there from Bennett. Is the MAC address table like a cache? Yeah, so it just, when it, so the question then is, how does it populate this cache, right? So we turned it on, it knew nothing. Packet came in, what did it learn from that packet? It learned by sending, it didn't know where to send that packet, but it did know where that packet came from. And it learned that I'm right here on port 2. And so we know that on port 2, we have MAC address BB22. So now when a packet comes in with a destination of BB22, it doesn't have to flood that packet. It can send it right out port 2. Usually the way MAC address tables work is they age out after 5 minutes. So every 5 minutes you'll see a kind of a broadcast occur, and then it'll rejigger its table and stick it back in. And when something moves to a different port, it changes its table around. You can muck around and confuse a switch if you're not careful. And I've learned that MAC address timers are really not something you want to fool around with either. I used to crank them way up high, and then that causes all kinds of problems. It causes packets to fall out on the floor because computers aren't there anymore, that sort of thing. All right, so how will this switch then learn eventually learn that on port 4 and 5, we have CC11. How will it learn those eventually? Anybody know? How about when the return traffic comes back? So when our answer comes back from that server, it will learn those and will put them in its table. All right, so now we get into a little bit different type of a device here. In Clemson's case, at the distribution layer. In other networks, that could be somewhere else in the network. But we get to our first router. And a router is a thing that handles what layer of the OSI model, typically? Any ideas? Layer 3, yes. So in our case, we have a packet that is destined for this Google IP address, 172.13. Whatever it was. Doesn't really care actually where it came from, but it's mostly important about where it's going. So a router has a table in it. Anybody know what that table might be called? Routing table. Very good. And that would typically have another draw. What would be the fields in a routing table? Any ideas? About prefix and next hop. In our case, this router might know that 130.127.4.0/24 is connected to, in this case, Ethernet 0/4 and 5. So this router understands that that network is actually configured on it, and it is actually on, in our case, we said ports 4 and 5. But what about Google's address here? What did we say that was? 172.13.228.28. What does this router have that's going to tell us how to get to Google, which is where we want to go? Any ideas? You think that this router in the equipment closet down the hall has got any clue how to get to Google specifically? No, we're not. We've done our name server resolution, you know, back, and we're now just with IP addresses. So other routers, yeah. Well, that's actually a really good take there. Other routers is a good idea. So it does learn it from other routers, can learn it from other routers, and that's via a mechanism called routing protocols. So these are protocols that routers use to exchange routing information with one another. Anybody know some examples of some routing protocols? So the earliest routing protocol, or the original, yes, Ospf, BGP, very good. The earliest routing protocol was one called RIP, which stood for Routing Information Protocol. It's mostly obsolete now because it did not pass information about subnet mask. In the early days, the first octet, whatever that was, told you what the subnet mask was, and that's where you hear terms class A, class B, and class C addresses. If whatever the first octet was told you what the subnet mask was. It was efficient, but it proved to not be scalable. Version 2 technically still works. OSPF, open shortest path first. There's IS-IS. There is that's some other ones. There's also BGP. They all, in the end, do the same basic function in that they say, hey, I'm a router, and I know about the following networks. And the other router says, okay, good, and I'll add that to my routing table. But I don't have to run a routing protocol. If I was a crazy network engineer, how could I run my network without a routing protocol? Any ideas? Craig, we have until 5:15, right? Okay. The answer is we could statically configure routes. So I can go on a router and I can put a static route in. One static route that's typically actually installed on a router is a default. And that might be the address of the border router or something like that. Or actually the address of the aggregation router in our case. So in any case, there's typically a default route, and that default route could have been put in via a routing protocol, or it could have been put in via a static route. What would be the benefit of using a routing protocol over a static route? Any ideas why a network engineer would choose to use a routing protocol as opposed to using a static route to, say, put a default route in? Maybe so, yeah. You want your network to be flexible. So as you need to change things, you want to not have to connect to 50 different devices and change it. You just want to change it in one place and have that change get distributed out to your network. You have to be very careful, because if you do that wrong, you can also turn your whole network off. Ask how I know. This router now has our packet, and it's going to send it out, and it knows it's got to put send the next hop to 130.127.0.2. But take a look at our packet here. Is there anything in there, anything in our packet that says anything about a next hop? Something in this packet has to change when it goes through a router. Does anybody have any idea what that is and why? That's a good try. Yeah, that actually does, the time to live does actually have to change. But what is the fundamental thing here that we can change that we can then cause the packet to start traversing the network? Yes, we changed the destination MAC address. Or rather, the router changes the destination MAC address. What does it change the destination MAC address to? The next hop, exactly correct. So that is what a router does, is it does what we call a layer 2 rewrite. So it rewrites the layer 2 destination so that that packet, say there's an Ethernet switch there between the router and the next router, it's going to get to that thing, and that Ethernet switch is going to have to make a decision, what port is that thing on, and it's going to send it or flood it, but it's going to get out that way. I mentioned before that that a switch always has to forward a packet, but a router does not. In what situation would a router not forward the packet? Any ideas? So the answer is, if it's not in this routing table, it's not going to forward it. If there's not a match, if it doesn't match a default, and keep in mind, a router does not have to have a default route. That's something that's added by humans. In fact, out on the internet, routers on the internet are called, another name for them is the default free zone, because there's either a route to it on the internet or there's not. There's no such thing as a default route. On my network at Clemson, there's default routes because we know not everything is at Clemson, and I don't need for all of my routers to have the entire internet's routing table on them. I just need to know, all right, you know, all your Clemson stuff is here and anything else that away. But on the internet, it's either there or it's not. So let's just say, imagine for a second that this router we're looking at does not have a default route on it, and that packet doesn't match anything in that routing table. What does it do with it? Well, doesn't send it back. It sort of does. It doesn't actually. What it does is it drops it. It does not forward the packet, and it sends back another packet. In our case, in this case, it uses a protocol. Anybody know what the protocol it uses to answer back and say, hey, I'm sorry, I had to kill your packet? The protocol is called Icmp, or the Internet Control Messaging Protocol. You may have seen this protocol used if you use pings or something like that. There's an Icmp echo request and echo reply protocols. There's also Icmp no route to host, Icmp time to live exceeded, that sort of thing. But the router actually generates a packet back to you and says, hey, dude, I'm a router out here and I had to kill your packet. There was no route to it, or the time to live had expired. Which brings me to another thing I like to talk about sometime. You guys maybe have used a protocol called Traceroute. Any ideas how Traceroute works? So if you type Traceroute, www.google.com, in a command prompt, you will see your computer derive at least one route to get to there. How did it elicit that? Then you got it. What it does is it sends the packet out. One element in the packet is called the time to live. And every time that packet passes through a router, that time to live value is decremented. And when the time to live gets to 0, the packet is dropped. So the traceroute application builds some packet and sends it out with a TTL of 1, gets to the first router, kills it, decrements to 0, and says, hey, I'm sorry, I'm a router and I killed your packet. Well, that's good because you just learned who that router was. Routers are not required to answer that. They should answer, but they don't have to. So if you do a trace route and you see stars, that's because there's a hop that is not answering time to lives, and that could be a misconfigured security configuration or a purposely configured security configuration. In my book, it's bad if you don't pass Icmp because the protocol exists to tell you what's going on the network. And when you see stars, it's because somebody's a moron, that's my opinion. So now, the packet moves through, we move through distribution, we move through aggregation. The exact same thing is happening every time we move through one of these routers. What's happening? It's changing the destination MAC address to the MAC address of the next hop, and that packet is just hopping along through all these routers. And there could be multiple ways to get to these routers, and the routers are just sending it in whatever way we have configured it to work. It may alternate round robin, it may always use one, it could be configured in multiple ways. We get to a firewall, these boxes here. What's special about a firewall as compared to any other type of network device? Any ideas? So the firewall is oftentimes called a layer 7 aware device. And that means that it can look at a packet at any of the layers and can make a policy decision on whether to send or not send that traffic based on whatever. If you wanted to drop every packet that contained the word Dan, you could build a firewall filter technically to do that, and any packet that had Dan in it would not pass through. Routers and switches, remember, they operate at layer 2. Routers typically operate at layer 4. Firewalls can make decisions at all sorts of layers. So we call that a policy device. At Clemson, I think our security folks would not like to hear me say this, but we are in the packet moving business. We like moving packets. I like moving packets way better than I like not moving packets. So we try to keep policy as much out of the network as possible. One of my favorite sayings from our chief technology officer here is that the network is not your mother. We just move the data. We don't care what the data is. Don't care. Assume if it originated or is headed in to Clemson's network, then it's important to somebody at Clemson, and we need to move it. We need to move it fast. So we get out here to the border. Oops. Get out here to the border. What's special that goes on at the border router as opposed to routers inside our campus? So we talked about routing protocols, and I mentioned to you that we use the Ospf routing protocol on campus. Any idea what routing protocol the internet uses? Any guesses? BGP, yes, very good. So here we are. Look at there, I put it in a different column. These protocols are called IGPs, or interior gateway protocols. And this protocol is called an EGP, or exterior gateway protocol. Anybody care to guess or know what would be the primary difference between those two? They both distribute routing information, but they do it in a different trust mechanism. So typically an IGP assumes, got it? An IGP assumes trust. So these are all my routers. The same group of people configures these. We're on the same page. We operate it as one system. The internet, though, I don't know who those crazy people are. I don't trust anything coming from them. So, in fact, I don't trust people unless I have a contract with them and I'm paying them money, usually. So if I contract with an internet service provider to carry Clemson's traffic, I say, hey, I want you to carry my traffic. Yes, exactly. I want you to carry my traffic, and I trust you, and I'm going to advertise Clemson's address space, which is in IPv4 land 130.127/16. So we have, it's an old class B, it's 16 bits of network address and 16 bits of host space in there. So I'm going to advertise to you 130.127/16 and some others, and I want you to give me back the whole internet routing table. And so they're like, okay, got it. So they build a routing policy that they'll accept this, only this set of prefixes from me, and I will set up my router so that I will expect the whole internet routing table to come in that way. And then these border routers will have a routing table, a little tiny routing table for Clemson and all the stuff that's there that it learned via its IGP, in our case Ospf, and an enormous routing table that it learned from that ISP that I just built a contract with and paid them money. You see my shirt, it says Internet 2 on there. So colleges and universities in the United States work collaboratively to operate a private network that connects almost all colleges and universities. If you send traffic from Clemson to University of North Carolina, it's actually not traversing the internet, it's traversing a network we call Internet 2. So, and that is just another set of networks that is connected to people who have, in this case, banded together with a membership organization and built a nationwide network that connects schools together at really fast speeds. So I turn up here to Internet 2, and I say, all right, Internet 2, I'm going to advertise to you 130.127/16 and some other ones. And from you, I'm going to expect 30,000 routes from the other colleges and universities. So now my router, my border router knows, okay, if I can, I'm going to send it out Internet 2 because that way's really fast and Dan configured it this way. And if I don't know how to get to it, then I'll send it out this ISP link and it'll get there somehow via the internet. So these clouds out here, they're actually called autonomous systems. In fact, this hole from right here, this is Clemson's autonomous system, which is 12148. That's our autonomous system number. Every autonomous system on the internet has got an AS number. But it's an abstraction. It makes it so that I don't have to care how C-Lite runs their network. I don't have to care how Google runs their network or Internet 2 runs their network. It's just a cloud that contains something that looks like we drew out. It could have firewalls, it could have layer 2 switches, could have layer 3 routers, that sort of thing in there. So inside of each one of these clouds here on the internet is the same stuff we just went over. It's just repeated over and over again. And the packet is layer 2 rewritten by routers and forwarded by layer 2 devices through there until it comes out on the other end. And it finally gets to some network that's like, oh yeah, that is over there on port 4 on this switch. And the packet comes out. So that is pretty much the life of a packet. Anytime after I do one of these things, I usually remember, dang it, I left a piece out somewhere in there. But for the most part, I think that's it. Does that make sense? Questions? Can you all go run a network now?
hopefully they can set up their network in AWS. I mean, it's already 2
Yeah.
projects in, so hopefully they have it set up and they're, you know, not turning in their projects.
Let's see. So let me turn on chat here so I can see it. Clemson set up to where all in-device packets have to go through the data center. Yes, they do. But in most cases, it's just a routing hop. We could, I guess, if we wanted to, we could add a link, you know, from the aggregation layers. But see, we really have to get it through this firewall layer because we want to apply policy and make sure that bad stuff isn't coming in or going out, right? So that's sort of why we aggregate it that way. But we didn't have to. We could build a bypass, and in some cases we actually do. There's some research cases that need to not flow through firewalls and have to have security applied in other ways, and we can do that. Sort of the part of the network that I have left out is most all of this network is abstracted and is actually running on top of other protocols like multi-protocol label switching, where this is all virtualized. So we can work all kinds of magic that way, but this is a good way to explain it. And again, it's just about layers and encapsulation, which we didn't really touch on, but you can guess what that could be. So, which is, encapsulation would be taking a whole packet like this and stuffing it into the data portion of another packet and sending it that way, and then having a device that can strip that packet out and stick it on there. So that's how, say, a VPN works as an example. So, other questions? Can I explain BGP again? So BGP is just nothing but a routing protocol. The only difference is that it's a routing protocol that assumes virtually zero trust. So whereas protocols like Ospf and RIP just learn about routers and trust whatever routers come back and say, or trust, there's a very limited set of security that I can maybe pass a keychain between my routers or something like that. But for the most part, they're routers in my autonomous system, so I trust them. BGP has no trust. Where you have to get careful, and I have 1 or 2 network engineers that are really good with operating BGP, in that they can manipulate it to cause traffic to come back certain ways. It's easy to make traffic go out one way, but if I have a link that's overloaded on an inbound side and another link that is less loaded, I have to convince the rest of the internet to send that traffic the other way. And so I can do that via making it look like it's longer to go another way. There's a lot of different magic that these guys understand how to do to cause the internet to send us traffic through different paths. Other questions? You're very welcome. So my certification, they're long since expired. I used to have a CCNP, but actually I didn't have one until I had been a network engineer for some time. To get the highest one is CCIE, getting a PhD. It's pretty hardcore. These days, though, I swear if you understand what I just told you and you can work through it that way, you could do pretty good. And when I'm interviewing a network engineer, I draw up a picture of our network and I sort of try to get them to talk me through how packets get through. And I can really tell. Some people get certifications and they just know how to configure things, but they don't actually think about how packets move. I think the trick with a certification is make sure that you are also applying your knowledge about how to configure the Cisco, Juniper, whatever devices. But more importantly, you're thinking about, okay, what did that configuration do to cause packets to flow or not flow in a certain way? Because then when your employer decides to switch from Cisco to Juniper or who knows what, you're not going to be clueless, and you're going to be able to sit down and figure out, okay, so how do I set a default route on
an extreme switch?
Or an extreme switch, yes. So, other questions?
If nobody's got any more questions, the quiz for today is on HTTP. That's what we talked about on Monday. You're free to use the docs and all of this stuff, and the password is, I believe today it's blue, all uppercase, and I'll put that in our Slack general chat. I bumped the due date out, or the due time out to 6:30, just so you guys would have a little bit extra time to do it. And if you have any more questions for Dan or I, we'll stick around for another couple of minutes. Otherwise, that's it. Get out of here. Have a good Wednesday.
You're very welcome. Yeah, thanks, guys. I'm glad it made sense. I always wonder when I get started, am I going to remember this, and is this going to make any sense to anybody? So I'm glad it seems like it has. So
is it unpublished?
Feel free to look me up. I'm glad to chat anytime, or you can come by if we ever actually get to be in person again or something. You know, in a large group, maybe one day in the future, we can actually take a look at some network closets and data centers and that sort of stuff. But feel free to look me up and get in touch. I was a Clemson student too. I just basically never left. So,
yeah, I know the feeling.
All right. Well, I've really enjoyed it, and we'll talk to you later.
Yeah, thanks for coming out virtually.
Yeah, anytime.
Thank you. What's the access code? It's in Slack. It's blue, all uppercase. Thanks, Max. I just opened it up, opened up the module. Somebody told me the module wasn't open. I think I got it. So it should be good now. What's a good way to refresh the browser via on-click property? Window location reload. Using bind. You just want to have a function, have the on-click go to a custom function you write, and have that custom function run the window location reload. All right, if there's no more questions, I'm going to end this here Zoom thing. Thanks again, Dan. And I'll be posting this video onto YouTube a little bit later tonight, so I'll send you a link to that. And if y'all have any questions, project's due tonight. Good luck. Hit me up on Slack. Bye, y'all.